Okay. So you had a graph that looked like this, right? And this was what kind of function? Rate of change function, right? And I asked you to talk about what's happening to the population, say, at 0.4 months. At 0.4 months. So what is happening to the insect population at 0.4 months here? We get this point is what, 0.4 comma 30? What's that?
It's growing at a rate of 30 insects per month.
She says the insects are growing at a rate of 30 per month. Is the insect population growing here?
Yes. Yeah.
Mostly yeses, some nos. This is a rate of change graph, right? So the rate of change is decreasing. But what about the population?
Still increasing.
Increasing because the rate is positive, right? So the rate is positive at 30 insects per month. So the rate at which it's increasing is going down, but the population itself is going up. So in the first month, when is the population the greatest? At the end of the month. Why? Because the rate is positive this whole time. The insect population is going up, 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 up. It's just at a varying rate, right? A varying positive rate. So the population has a maximum in the first month at 1 month. At 1 month. Okay? If you're just looking at that first month. Okay? And so then I had you graph a constant rate for 0.2 months at 25, at 45, and at 60. And I said, does any of these best relate to the actual rate of change, what's happening with the rate of change in the first 0.2 months? Do any of these do a better job or than the others to say maybe what is the rate of change in the first 0.2 months? What's that? Okay. The middle one, right? So what do you notice about this rate of change down here? It's lower than the rate of change for the whole time. And what about 60? It's higher. Okay, so maybe if we were just trying to say, what would a single constant rate be to kind of reproduce the rate of change in these first 0.2 months, we might pick something kind of in the middle of all the range of rate of change that we see there. So maybe this one here in the middle would be like, this is kind of like the best we could do if we were going to simulate the rate of change function with a constant rate. And why do we want to do that? Why, if we have the actual real rate function, why do we want to simulate it with a constant rate of change? What's that?
It's easier to do.
To do, right? So because we know the math of constant rate of change is really easy. M dx, right? You get a little change in y by m dx. As soon as the rate is changing, that's off the table, right? You can't use m dx anymore. But if you've got a constant rate of change, you just take that constant rate times your whatever your change in x is, and that gives you the corresponding change in y. Okay? And so then in the last activity in that homework, you were asked to come up with some way of approximating the total change in the insect population, and so we can continue to do that. We can continue to do that. This is just one way of doing that. In the second 0.2 months, I estimated it at something like 42 or 42.5. And then likewise in the next 0.2 months, somewhere a little bit more than 20. And then in the next 0.2 months, maybe 16-ish. And then for 0.8 to 1, maybe 24 or something like that, insects per month. Okay? So what are we doing? We're taking this changing rate function and we're kind of making a new rate function that's trying to be like that one, but with constant rates, right? It's trying to mimic or reproduce that with constant rates so that we can use our constant rate of change math, which is really easy, to come up with some total amounts of insects, right? So when you see this, you might start thinking about something like this, making rectangles and shading them in, okay? That's not what we're doing. That's not what we're doing. What are we doing? Because now what are we doing? We're coming up with a pretend rate function. We're not building rectangles and finding areas. Insects, this context has nothing to do with area. What it has to do with is using this rate function to figure out how many insects we have. So the first thing we do to do that is we want to come up with a simulated rate function. Using constant rates. This is a key point, and this may be a different experience than what you had in Calc 1. Okay, so again, not this. This isn't what you should be thinking. If that's where your thinking was going, change your thinking. We're creating a new function. We're not making rectangles. We're creating a new function that's trying to be like our given rate function, but made up of constant rates. Okay, and with that, we can come up with, say, for the first month, we can come up with some kind of estimate for our population or the growth of the population. So we can call this, say, M1, M2. These are our constant rates. Okay, and so M1 we say is 45. So what's the change in the insect population in those first 0.2 months? It'd be that, right? And the change of the population in the second 0.2 months? And then we can just add them, right? We got a little change in the first 0.2 months. We can get that by MDX. And then we got a little change in the second 0.2 months. And we can just add that on, right? So we can go all the way. Until, in this case, did I have 5? So what does this give us? The total change in the insect population based on our approximating function, right? Or an estimate function that's these constant rates.
Don't you need to add 105? Because that must be enough
So this is the change. This would be the total change in population, right?
without the 105. Because we started at 105, right?
But isn't this the change in the insect population?
Oh, okay.
How much it changes?
Oh,
So it depends what you want. Yeah, if you want the actual population, then you're going to have to add the 105. But if you're just asking for how much did it change in the first month, then it would be this, right? Okay, and so because those all look the same, we keep doing MDX plus MDX plus MDX over and over again. We've got notation to make that simpler, right? They're all MDXs. And we're just adding a bunch of them together, right? And so that's this symbol right here. What does this mean? This is sigma, which is Greek for sum, right? It's just the only thing that changes is the rate each time. So I could call this like J or something. And then my J is going to start at 1 and go to 5. So what does this say? It says let J be 1. And then calculate M1 dx. And then let J be 2 and calculate M2 dx. And then let J be 3 and calculate M3 dx. And then add all those together, right? That's what that says. Sum up a bunch of these. Sum up a bunch of MDXs. Really important. Okay, and so and what do you get? So, and all these dx's are 0.2, and then if I just put in the m's that I'm pulling off here, so 45, and then 42, M3, say 21, M4, 16, and M5, I don't know, 23. So I'm going to take 45 times 0.2 42 times 0.2, 21 times 0.2, 16 times 0.2, 23 times 0.2, and that's what this calculation is. Anybody remember about what that turns out to be? Did anyone do kind of this way? 131? Anybody else get something like that? So 133, sure, something like that. What are the units? Insects per month? Yeah, this is a change in the population. This is that the population went up by 133 insects. That's not including the initial amount, right?
No, that is.
So what was the initial?
Oh, equal by 30.
28, 29.
Okay. All right, so does this principle make sense? So there's both the principle of it, that we have a changing rate function. In order to figure out how much the total quantity has changed, we need constant rate of change, so we break it up and we make a new function that's pretending to be the changing rate function, made up of constant rates. And then for each interval, we can use our constant rate of change to get the little change in our quantity and add those up. And then here's the notation for that. Okay, so another way to make the pretend function here, the way we made the pretend function here is we just did our best at eyeballing. Like, what is kind of the middle rate of change or the average rate of change for that interval? So another way to do this is to just use the actual rate on the left side of every interval. So this is called a left-hand approach to, say, a left approach. To forming the constant rate pretend function or simulation function. And so what's the advantage to this? Well, you don't have to eyeball anything. You purely use the actual rate at the left side of every interval to be the constant rate for that interval. Okay, so there's no eyeballing, and it's just systematic, and everyone will get the same answer if we do it this way, right? So everyone will get the same estimated change in insect population if we do it this way. Okay, and so again, but it's the same thing. We're still gonna the only difference is where we get those constant rates now. We're getting those constant rates from the actual rate at the left side of the current interval. Okay. So questions on that? Questions on that? Okay, so let's go back and review. We're on this journey of making sense making sense of the fundamental theorem. So and we said principle 1 was constant rate of change. What does 60 miles per hour mean? What does 60 miles per hour mean? It means that every hour you go 60 miles. Is that what it means?
More than that. So much more than that.
So much more. Tell me. So much more than that.
Oh, well, it's a rate of change, right? Therefore, you know that in any moment you're going 60 miles per hour, but you could substitute any hours, or even any miles to get hours. Is that?
Okay. So what was the specific thing we said in terms of?
It's a constant rate of change that can be applied at any interval of time, and you get the same distance. And you get the corresponding amount of distance.
Okay, so you wait, right. So it's not just for 1 hour, but any amount of time. And so in 2 hours, how far do we go? And how did you get that? You did 60 times 2, right? And in 1/3 of an hour, how far do you go? 20 miles, because you took 60 times 1/3, right? And in 10 hours, how far do you go? Because you took 60 times 10. All right, so you're applying this principle we're saying is our bedrock for constant rate of change. You're taking 60 times the change in time to get the change in distance. So for any change in time, the change in distance is 60 times the change in time. So that's our dy equals mdx. Okay. This is like the foundation of the fundamental theorem of calculus. Okay. Principle 2 was that most realistic rates are usually changing rates. Usually changing rates of change. So here was our flag lowering, right? Here's our flag lowering situation. And principle 3 was to make a pretend rate function. And what was the characteristic of the pretend rate function? Why did we want to do that? Why did we want to make a pretend rate function? Okay, we want to simulate the changing rate function. And why do we want to, if we have the actual rate function, why do we want to do that? Make it easier. And what's that simulated rate function like? Yeah.
I was going to say a series of constant rates of change.
Right, so it's based on constant rates of change. We're going to make a simulated or pretend rate function. We're going to mimic the rate function with constant rates so that we can still use principle 1. So we can still use this idea of dy equals mdx. So what would that look like for the, all right, so then the total change equals m. So delta x is now when we're fixing these changes. Not so much a variable anymore, but just we're going to pick, like we picked 0.2 for the insect problem. So let's take a look at that for the this pretend rate function. Just pause here and take a look at that for the flag lowering situation. So here's the flag lowering rate function. Okay, that's the actual flag lowering rate function. Most of the time, the flag is cruising down at 0.75 meters per second, but then in between changing hands, it slows, it pauses momentarily. So the rate kind of goes to 0 momentarily and then back to 0.75 when the next hand pulls. Okay. So let's take a look at a potential. Here's a pretend rate function for 0.3 seconds. For 0.3 seconds. How's that doing at pretending to be the rate function? So by looking at that, could you tell what the rate function is like?
No.
Other than a lot of the time it's 0.75, not really, right? So that's kind of showing you that a lot of the time it's around 0.75, but it's not really showing you, it's not really doing a good job simulating the actual rate function. So how can I do a better job simulating the rate function? Yeah. Yeah. So if we took smaller intervals, so here's 0.1879. Maybe you could argue it's a little better, but you still probably wouldn't be able to sketch. So what about even smaller? So here's 0.0876. So now if I take in intervals of time of 0.09 or so, now this is starting to show what that original rate function looked like. So what if I want a really, really good approximate simulated rate function? I just want really, really small intervals, right? Smaller intervals gives you more accuracy. So what you're looking at here is still a bunch of constant rates. It's just the interval is super small, 0.01. But those are still all constant rates. So, so what happens? To get a better simulated rate function, we can just take small intervals. I think I can make it a little bit smaller. There's 0.005. And so then there comes a point when it's kind of like it's so small that we can't tell the difference. That the interval we choose is so small that we pretty much get exactly the original rate function. Question over here.
Yeah, do the intervals always have to be the same amount?
They don't. It just makes it easier. Like when you're calculating, when you're doing a problem. But no, absolutely not. You could vary it, and you'd still be coming up with a simulated rate function. Yeah. So in this that's actually a good question for this particular function, because like down here you're saying like for 0.4 seconds you could have a 0.4 second interval and then make the interval small through here and then big. Yeah, it's good. That's a good thought. Yeah, and that's perfectly valid. Yeah. Okay, so then we just think if we made the interval small enough, we essentially have the rate function made up of really small constant rates, and there's essentially no difference. Okay, so then we can think of, with really super small intervals, we can think of that our simulated rate function is actually reproducing the actual rate function. So back to our PowerPoint here. Principle 3 is a pretend rate function. And then to get the total change in the pretend rate function, this is what we said, we're going to sum up all the individual changes that we use. We use principle 1 for to calculate m dx plus m dx plus m dx plus m dx. Okay, so now principle 4 is what? Make the rate function better, more smaller intervals. So a better pretend rate function will mean a better estimate of the total amount, because that pretend rate function is mimicking or simulating the rate function better. So better rate function, better estimate of total amount. Better ingredients, better pizza. Papa John's. Okay, so then the principle 5 would be, okay, well, let's just keep going, right? So let's do really well. And so with super small intervals, we can think of our estimate of total amount as truly the exact total amount. Okay, so this calculation, when we're summing up all those little changes to get the total change, right? When intervals get small enough, we have a different way of representing this. So how do we represent this now with super small intervals? It's the same thing. We're still summing up a bunch of changes that we calculate by constant rate of change, but the intervals are super small. So how do we distinguish and represent that? Yeah. Yeah. So this is Greek S for sum. Integral is German S for sum. Okay, they're both are an S. Sigma is an S, and an integral sign is an S, standing for sum. The things they never told you, right? This still means sum. Is the German S, which means sum. And then what else is the same? Look, we have m times their change in x. Do we see that over here? So when the intervals are really small, we just, instead of having these individual rates, thinking about individual rates, when the intervals are really small, it's just the rate profile, right? It's the whole changing rate profile. That's what the function is. So this is our m, but it's just kind of like every single m, right? Think of it as every single m. And then the change in x, right? So m times change in x. Red just to get some different. So an integral expression is exactly the same as sum of m delta x, summing up a bunch of little changes. It's just for super small intervals. But it's the same. It represents the exact same thing. So here, notice, dx is not just a signal to tell you you're integrating with respect to x. It's part of the math. It's multiplication. It's f of x times dx. It's not just there to say, oh, look, we're integrating with respect to x. Right? It's part of it. We have to have that times dx, which then makes a small change in y. Right? So the product of those two things makes the change in y. So key point here. We're not summing up rates. This is multiplication. We're summing up products. We're summing up rates times changes in x, rate times change in x, rate times change in x. Just like in the insect thing, right? m1 dx plus m2 dx plus m3 dx. It's just, we're doing the same thing, but we're summing up a gazillion of them with really small changes in x. Okay. So now we need, so basically now we've made sense kind of the left side of the fundamental theorem there. Okay, we've made sense of the left side of the fundamental theorem, that it's the sum of lots of little changes, and those changes, we use the rate function to get little changes using the rate function. We're summing all those up to get the total change. Okay, so now let's go on from there. So here we are. And so let's now talk about, what about the height of the flag function? So this is our rate function on this side. Rate of change of height. And what about over here if this is a height function? So given this rate of change of height function, can you sketch what the height function is, say if the height starts at 5 meters? Suppose the height of the flag starts at 5 meters. Sketch the height function based on the rate. So using this rate function, can you sketch that height function? Go. Give it a shot. So if the flag starts at 5 meters, can you conceptually sketch what that height function would be given what our rate function is? Down on yourself.
That's important. You don't want to go 2 times.
Have fun at Target. Okay, how's it coming? Let's see.
It's pretty rough.
Yeah, so lots of people have got the right idea. Good. So let's see it emerge here. happens when the soldier changes hands? What happens to the height? It pauses, right? It doesn't come for that split second. It's not coming down. So generally coming down at a constant rate, but then there's those pauses where they're switching hands. So this is, as time goes by, this is how the height would come about. Something like this. Okay, so let's take a look at a time interval here, say from, who knows, 1 second to 2.5 seconds. So let's focus in on a time interval between 1 and 2.5 seconds. So x changing from so this is what we'll call r sub h. So this is the name of that function. And then this one will be h. Okay, so that the rate function r sub h and the height function h. So now what I want you to do is I want you to express in two different ways the change in height of the flag as x changes from 1 to 2.5 seconds. Okay? So express in two different ways the change in height of the flag. And this is exact actual change in height of the flag starting from 1 to 2.5 seconds. So just as a hint, one of those ways will be based on the rate function. And one of those ways that you express that change in height will be based on the height function. Okay, so that's your task. So what did we say? 1 to 2.5? So in two different ways, we're going to represent the change of height of the flag from 1 to 2.5 seconds. And my hint was, one way we'll use the rate function, r sub h, and the other we'll use h. And then when you're done thinking about it, talk to somebody else only if they're done thinking about it. Okay? So if someone is still working on it or you're still working on it, keep working on it. But if you can find somebody else, you're done, and you find someone else who's done, then why don't you talk about your two different ways of expressing this change in height.
Did you draw the height function analytically or numerically?
This one?
Yeah.
Graphing calculator is using that simulated rate function with a super small. That's why it took so long.
Cool.
But that's a good point because it's so so exact, even for that small, like 0.01. Okay, so we're done thinking about it? Everyone's done thinking about it? So let's start with the one on the left first. So using the rate function, how can you express the change in height of the flag from 1 to 2.5 seconds? This is actually what we've been working on, right? This is what we've been working on. So how can we do that? I bet you know. I bet you know someone I call. How about in a purple shirt? Did you come up with it?
Yeah, I mean, I was just going to go back to the station number 5, which was
Okay.
And it's actually made easier now that we know that we can do different p of x's.
Okay.
Because you have the same p of x for the up curve and the down curve, and then also for the straight lines.
Okay.
So if you want to get the middle, so it would be that first curve, the p of x would be 0.4.
Okay.
And you would, your rate of change would be about negative 0.38.
Okay. So we want to use like so that we've went further than that. So we want to use like everything we've done up till now to write this expression. So we want an expression that will give us that exact change from 1 to 2.5, and it involves all that. But we want to just go right to the punchline. What's that?
With the sigma or sum,
Okay. So we want the sum from.
1 to 2.5.
And if we want the exact, do we want sigma? So sigma is like if we have the discrete intervals, but now we want exact, right? So we want the super small intervals. So we want to sum up. So she's talking about summing up changes, that's right. But we want to sum them up when they're super small. And we're going to sum up what? What is it we're going to sum up? RH of right? We're summing up the rates, right? Summing up the rates. We're not summing up rates. We never have summed up rates, and we never will. Doesn't make sense to sum up rates. What are we summing up? Little changes in y that we get from the rates of change. And so how do we get a little change in y? This is times. This is multiplication. Times dx. That is multiplication times a little change in x. So this expression right here sums up all the little changes starting at 1, ending at 2.5. Sums up all the little changes which we calculate by m dx. Just like we did sigma m dx and added up a bunch of finite changes. Now it's kind of like they're really, really small, and there's a whole bunch of them. Okay, so now we're going to come over here and use the h function to represent that same change from 1 to 2.5. So this, what the h function gives you the height at any given time. So how can we use the h function to represent that same change in height? I know that. How about in the back there?
H of 2.5 minus h of 1.
Final height minus initial height. How many, before I started talking, after you were working on it, how many had got it? Got them both? A handful, okay? Or how many got at least one of those two? More, okay. So, yeah, so using the rate function, that's what integral is about. Summing up all the little changes, bit by bit by bit. Here we have the height function, so we can just take what's the height at the end, and then final value of the quantity minus the initial value of the quantity gives you the total change. We don't care about what's happening in between because we have the final height and the initial height. We can just subtract. How can I represent that change on this graph over here visually? How can I visually represent this change on this graph? Think about that. Think about that. How could I show some kind of visualization that denotes this amount of change? Okay, so where's y final? Y final is h of 2.5. So that's represented where? Here's 2.5.
And then just go up to the y value at 1.
So how is h of 2.5 represented here? Where would I get that value if I was looking at the graph? Y-axis, right? So it'd be like right here. Just below. It looks like it's just below 3.5. Something like that. And then h of 1 looks to be about 4.3, 4.35, something like that. So what is that change in height? Isn't that change in height, we show it like this right here? And that change in height is negative, right? So maybe a down arrow like that. So that arrow represents that amount of change from starting at h of 1, which is about 4.35, ending at about 3.45, which is h of 2.5. And that amount of change we can also represent with the integral from 1 to 2.5 r sub h x dx. Does it make sense? All right, so therefore, if what's in this box is representing the same amount of change as what's in this box, what can we say? They're equal, right? Those are equal. So two different ways to represent the same change in a quantity, using its rate function and a million little changes summed up, or using the actual quantity function and just looking at where it ends up, where it started, and finding that change, the difference, right? So those are equal. Okay, so then the last thing we have to know is what is the relationship of this r sub h function and the h function? Should have just circled that much of it. What is the relationship between r sub h and h?
H is the antiderivative of R H.
Okay, so we can start by saying that r sub h is derivative of h because it's this rate of change, right? So r sub h is the derivative of h. So that therefore, what he said that h is the antiderivative of r sub h. Okay, so a quantity function is an antiderivative of its rate function, right? The quantity function is the antiderivative of the rate function. So now we have everything we need. So we just put it all together. We have the whole fundamental theorem here. We understand integral. We understand there's another way to express that change that the integral is giving us. And we just know that we just need the quantity function, which is the antiderivative of the rate function, and we can express that change as final value of the quantity minus initial value of the quantity. Okay. So let's summarize that. So we're at the last two principles. So this, what we just did was principle 6. Two ways to represent an amount of change. Okay? We can use the rate function and an integral, right? We can use it, and that's what we spent the last day and a half doing. Building up the idea of integral. That it's the sum of lots of little changes. Each one, the product, rate times change in x. Okay? Or we could just plain out use the quantity function and just find the final value of the quantity minus the initial value of the quantity and subtract. And so then principle 7. So looking at that, principle 6, right? Over here on the left, using the rate function and the integral. Or using the quantity function and just taking final minus initial. And then finally, it's the relationship of capital F and little f. Quantity function f is, I should say, an antiderivative. There's functions have more than one antiderivative. Quantity function of f is an antiderivative of the rate of change function of little f. The rate of change function of little f. And so that makes sense of the whole thing. So we started with rate of change, and we ended up with the meaning of that equation, the meaning of the fundamental theorem. The things they didn't teach you, right? So important, so important. So here's a notational thing. This total change of using the quantity function can be expressed this way. You just write the function f, and then a to b with a vertical line on the right. That's another way to express those mean the exact same thing. So let's just do this first one. Do it with the person next to you. So do A, B, and C. So A is explain the meaning of the expression. Include all these specifics. What is based on what we've done in the last 2 class periods? What is the whole meaning of that thing? And then write a computable expression that gives its value exactly, and we won't even do C. So let's just work on A and B, and we'll be done. So this I want you to work on. Recitation. This thing right here. So you can just write those down.
Do you want me to grade those?
Yes.
The new ones.
Yeah, I have. Grade these.
Yeah.
It's up to you. It could just be an activity. You can go over at the end and let them keep it. If you don't want to grade them, it's totally fine.
It's printed out enough for Wednesday too.
Oh yeah, good,
We
good.
could do Friday.
Okay. Who thinks they can explain the meaning of that? Based on what we've learned in the last couple days. What does that whole expression mean? Want to try? Yeah.
It's the quantity, function change.
Okay. There's a little bit more to it. Yeah.
Find the change in y of function f if x to the 4th is the rate of change of function f.
Okay. Anybody else? This is both good, but both were all very close or all right. So what is that? That is the total change in some quantity, right? As x changes from 1 to 2, when the rate is x to the 4th. That is giving you that is expressing the total change in some quantity as x changes from 1 to 2 when the rate function is x to the 4th. And how can we find out that total amount of change? By using the other way of computing it, which is final minus initial. And what is capital F compared to x to the 4th? X to the 4th is the rate of change of capital F. So we need the antiderivative. We need a function whose derivative is x to the 4th. The antiderivative will be the quantity function for the rate x to the 4th. 1/5 x to the 5th has the rate of change x to the 4th. And then we want to take, that's our quantity function. So we're going to find that at 2, final value of the quantity, and then the initial value of the quantity, and subtract. So that is that total change of the quantity from 1 to 2 with a rate of change of x to the 4th. Make sense? So you'll practice more of those in recitation, and then he's also got an activity for you. And then homework is posted on Blackboard for Wednesday. There'll be more written homework for Wednesday.